With a sign O9A number 10. A proton is projected in the positive x direction into a region of uniform electric field. E is equal to negative 7 times 10 to the 5th I hat newtons per coulomb at time equals 0. The proton travels 6.9 centimeters as it comes to rest. A. Determine the acceleration of the proton. B. Determine the initial speed of the proton. C. Determine the time interval over which the proton comes to rest. Alright, so the problem states there's an electric field in the negative I hat direction, which is going to point to the left. And it tells us that the distance the proton travels before stopping is 0.069 meters. And from our previous knowledge, we know that the mass of a proton is 1.69 times 10 to the negative 27 kilograms, and that it has a charge of 1.602 times 10 to the negative 19 coulombs. And it tells us that the proton was shot in the positive x direction, which is why the original velocity is pointing to the right. But since this is a negative electric field with the electric field lines pointing to the left, the proton's actually going to accelerate to the left because protons always accelerate in the directions of the electric field lines. So the first part, part A, asks us to find the acceleration of the proton. So we know that force is equal to QE, but from our previous knowledge we also know that force is equal to mass times acceleration. So from here, dividing both sides by the mass, we get the acceleration is equal to QE over m. Simple enough. So just writing this all out, the charge for a proton is 1.602 times 10 to the negative 19 coulombs. And the electric field strength is negative 7 times 10 to the 5th I hat newtons per coulomb. And again, the mass is 1.67 times 10 to the negative 27 kilograms. This results in an acceleration value of negative 6.175 times 10 to the 13 meters per second squared. And this negative sign here just tells us the direction, which is going to be to the left. Part B asks us to find the original velocity of the proton. So we got to start off with one of our kinematic equations. Vf squared is equal to Vo squared plus 2a delta x. Except when the proton comes to rest, it's not going to have a final velocity. So we could say that Vf is equal to 0. So doing some algebra, we get the original velocity is equal to the square root of negative 2 times the acceleration times the displacement. Let's plug in our own values. We got negative 6.175 times 10 to the 13 meters per second for the acceleration. And our delta x is 0.069 meters. This results in an original velocity of 3.044 times 10 to the 6 meters per second. Now for the last part, it asks us to calculate the time it takes for the proton to stop. So we're just going to start off with another one of our equations. Delta V is equal to AT. Divide both sides by the acceleration. Here the delta V is going to be the final velocity minus the initial velocity, which is 0 minus 3.044 times 10 to the 6 meters per second, resulting in negative 3.044 times 10 to the 6 meters per second, divided by our acceleration of negative 6.175 times 10 to the 13 meters per second squared. This results in a time of 4.533 times 10 to the negative 8 seconds. This problem was challenging because I thought that a proton in an electric field would accelerate infinitely and would never stop and just keep accelerating. But I realized that if its original velocity is in the opposite direction of the electric field, it will accelerate in the opposite direction and have to hit a point where it comes to rest before it accelerates in the other direction. And this problem shows my growth because it shows that I understand how charges behave in electric fields, and shows that I'm able to calculate the force and acceleration of a particle in an electric field. It also shows that I still remember those good old kinematic equations that we still use almost every day. Also, side note, I ended up cleaning the board, so it should look clear.